Good day, students. Welcome to our class. I am your science teacher, Sir Roy M. Capul. For today's lesson, we are going to discuss Charles Law. Let us begin with our lesson map. First, we are going to familiarize ourselves with the scientist or the person behind this particular law, who is Jacques Charles. Next, we are going to discuss what is Charles Law all about, and we are going to apply the formula for Charles Law in a sample world problem. Next, we are going to appreciate the different application of Charles Law in real-life setting. Let us begin. Who is the scientist behind Charles Law? He is none other than Jacques Charles. He was born on November 12, 1746 in France. He is considered to be a French mathematician, a physicist, and an inventor. About 1787, he developed Charles' law concerning thermal expansion of gases. According to Jacques Charles, as the temperature increases, the volume of gas also increases. And as the temperature decreases, the volume of the gas also decreases. Now that we are already familiar with Jacques Charles, let us discuss Charles' law. By definition, Charles' law states that at constant pressure, the volume of a confined gas is directly proportional to its absolute temperature. In this particular definition, there are two variables or concepts in science that were highlighted. We have the temperature and the volume. What is the difference between these two variables? When we talk about the word temperature, it refers to hotness or coldness of the gas molecules. The unit that we usually use is Kelvin, or symbol of letter K. Mean to say, if the problem gives us a temperature which is expressed in degrees Celsius or degree Fahrenheit, we need to convert it into Kelvin. Next is volume. It is the space occupied by the gas. The unit could be liter, milliliter, cubic meter, or cubic centimeter. To discuss it further, let us analyze this particular illustration. You will observe that after placing the inflated balloon in a container with very hot water, the balloon will expand or increase in volume. However, removing the balloon from this container will bring back the balloon to its original size. Now, let us discuss the relationship between the variables in Charles' law. In Charles' law, volume is directly proportional to temperature. It means that as the volume or as the temperature increases, the volume of the gas also increases, or vice versa. Therefore, the general formula for Charles' law is equal to V1, or the initial volume, divided by the T1, the initial temperature, is equal to V2, the final volume, divided by T2, or the final temperature. If the initial volume, or V1, is missing, the formula is V1 is equal to V2 multiplied by T1 divided by T2. If the initial temperature is missing, therefore the formula is T1 is equal to V1 multiplied by T2 divided by V2. If the final volume is missing, V2 is equal to V1 multiplied by T2 divided by T1. And if the final temperature is missing, the formula is T sub 2 is equal to V sub 2 multiplied by T1 divided by V1. So here are the different formula that you can use in order to solve word problems. Now that we are familiar with Charles' law, let us apply the formula in sample word problem. Given this particular problem, under constant pressure condition, a sample of hydrogen gas initially at 55 degrees Celsius and 4.2 liter is cooled until its final volume is 2.1 liters. What is the final temperature? In order to solve our problem, let us always follow this format. Look first for the given, next formula, then solution, and then let us write the final answer. Let us begin with the first step, which is finding the given. Based on the problem, we have the initial temperature or T sub 1 is equal to 55 degrees Celsius. Then, also we can see that the initial volume is 4.2 liters. We also have the final volume or V2 which is equal to 2.1 liter. Therefore, the missing variable in our problem is T sub 2. However, let us always remember that in solving Charles' law, the temperature should always be in Kelvin. So let us first convert T sub 1 into Kelvin. So 55 plus 273, that is equal to 328 Kelvin. Now that we already have the complete given for the problem, let us proceed to the next part, which is the formula. In the problem, we are looking for the final temperature. So the formula would be T2 is equal to V2 multiplied by T1 divided by V1. The next step is solution. By using the formula, let us apply or let us substitute the given in our formula. T sub 2 is equal to 2.1 liters multiplied by 328 Kelvin divided by 4.2. By looking at this equation, we can already cancel similar units, and that is liter. Now, let us first solve for the numerator. 2.1 multiplied by 328, that is equivalent to 688.8 Kelvin. Divided by 4.2, we will arrive in the final answer. And the final answer for our problem is T sub 2 is equal to 164 Kelvin. That is our final temperature. Now, let us proceed to the different real-life application of Charles' law. The first real-life application is all about the hot air balloon. The working principle of an air balloon is simple. It is consists of a bag or an envelope, a basket to carry the passenger, and a fuel source like propane. On ignition of the fuel, the air inside the envelope heats up. The hot air expands as per Charles' law. As the temperature of the air increases, the volume of the air also increases, and consequently, the density decreases. This causes the hot air balloon to rise up. Next is the pool floats. The air in swim floats shrinks because of a decrease in temperature of the air inside the float. So this happens when the water is cooler than the air. The reverse phenomenon is observed during hot summer days when water is much warmer. In a hot climate, the temperature of the air inside swim floats increases and they get overinflated. Next one is all about the tires. The tires of untouched vehicles get deflated during freezing winter days while get inflated in hot summer days. This is caused by Charles law. In winter, due to low temperature, the air inside the tire gets cooler and they shrink, while in hot days, the air expands with temperature. The next application is the helium balloon. Like tires, helium balloon also experience expansion and contraction with a change in the surrounding temperature. If you take a balloon out in a snowy day or in a winter season, it crumbles. When the same balloon is brought back to a warm room, it regains its original shape. This is the coverage of our lesson for today, and here are the different references that I made use for this particular presentation. Thank you so much for watching.